All right, for example 3, it says find y prime if x cubed plus y cubed equals 6xy. We'll notice that this is a implicit function because we have x's and y's all throughout the equation. There's not y equals everything in it. What I want you to notice about this is each specific term has some sort of a structure, and that structure establishes what derivative rule we're going to use to differentiate. We have x to the third power, which is just a basic power function. We have y cubed, which is plus y cubed, which is a basic power function. And then we have 6xy, which is a product of 6x, a function of x, and y, a function of y. And that makes it a product, so we'll have to use the product rule to differentiate that. So we have power rule, product rule. So if we start off with the first one, the x cubed, the power rule, right here. The derivative of x cubed is 3x squared. And with implicit differentiation, you have to ask yourself each time you differentiate, am I differentiating about x or y? And we're always going to do it with respect to x, but if we differentiate x, we're going to just get the derivative as is, no extra features necessary. If we take a look at y cubed, it's plus y cubed. The derivative of y cubed is plus 3y squared. Again, just the basic power rule. We take the power times the letter to one lesser power. But now we're differentiating y against x, so we have to put a dy dx next to it to account for the fact that we differentiated y instead of x. So again, if I differentiate x, I get the derivative as is, just like it's happened every chapter so far in the book involving derivatives. If I'm differentiating a y expression, I'm going to get a dy dx next to my derivative. Then there's an equal sign, and then my 6xy. So if I focus on, first off, 6x we'll say is function number 1, and we'll call y function number 2. And the product rule for differentiation says 1d2 plus 2d1. I forgot to use a different color there. Like so. And what I need to get across to you, and the thing that typically upsets or maybe confuses calculus students here at the beginning of this section with implicit differentiation is, I just got done saying when we differentiate y, we put a dy dx. When we differentiate x, we put nothing. We just get the derivative. And what students tend to see is that when there's a y in the answer, we put the dy dx. When there's an x, we don't. With product rule and even the quotient rule, sometimes you'll get an x with a dy dx or a y without. And it really depends on what we're differentiating. So when we look at the product rule, this is a derivative, and this is a derivative. This is just write something down, this is just write something down. When I'm just writing something down, it has no bearing on the derivative. So when I do 1, which is 6x, that's just writing down 6x. I'm not doing anything to it, there's no calculus involved, I'm just simply writing down that piece. That's the first part of this term. d2 is the derivative of y, which is 1. Y is just a variable to the first power. Derivative variable to the first power is always 1. But what I'm differentiating is y, and I'm differentiating with respect to x, so I've got to put a dy dx because I differentiated y. Again, there's x in the term, but the derivative is happening here, and it's all about what I differentiated, not what the term looks like. And then when I do plus 2, 2 is function 2, which is y, and d1 is the derivative of function 1, which is 6x. The derivative of 6x is 6. Just like it always has been. Notice I'm differentiating this object. This object is an x object. The derivative is 6. No extra added features necessary. Even though there's a y in the term, this does not get a dy dx on it. Again, it all comes down to what am I differentiating, which letters involved in the derivative when I do that actual step. That's the calculus step of that problem. Everything from this point forward is going to be algebra. My recommendation would be to simplify as much as possible. I don't want to get parentheses in anything. So 3x squared is simple, 3y squared dy dx, that's all together is simple. I've got some parentheses here and here, so I probably want to make that a little bit prettier. So I would go on and say 3x squared plus 3y squared dy dx equals 6x dy dx plus 6y. So we'll get the expression as simple as possible. Again, 1d2, this whole product is one term. 2d1, that whole product is one term. So 6x times 1 times dy dx just makes 6x dy dx. Y times 6 just makes 6y. At this point, my goal is to figure out what dy over dx equals. Every term containing dy over dx, you can see the dy dx is there. The 3y squared is attached to this one, and the 6x is attached to that one. I need to get those terms together on one side, the other terms on the other side. And I personally like my dy dx to go to the left. There's no set rule, you have to go this way or that way. But I'm going to take the 6x dy dx, move it to the left. I'm going to move the 3x squared, move it to the right. So 3y squared dy over dx stays right where it's at. Minus 6x dy over dx moves across and therefore changes from positive to negative when I move across the equal sign. Then I write the equals down. 6y is staying where it's at on the right hand side, so it stays positive. 3x squared moves where it becomes negative 3x squared. Next, I've got multiple terms here with dy dx. So yesterday when we saw these problems, we just had something dy dx equals, and we just had to divide by the something. Now we got multiple pieces, both containing dy dx, and we can have multiple. You can have 3, 4, 5, 6 different things over here. Everything here has a dy dx on it, which makes dy over dx a common factor. So I'm going to factor it out. 3y squared minus 6x is the uncommon pieces times the dy over dx, which is the common piece. When I do that step, nothing happens to this side. You should still bring it down. All right, so make sure you always, in your nice organized work, you're always bringing the problem down as you go. And then dy dx is what I want. I've got something being multiplied by it, so I'm going to divide both sides by that something. That gets me here. Those cancel. Dy dx equals that. And typically that's it, the end. End of story. Problem's done. In this specific case, and something you should notice, 6 and 3 and 3 and 6 all divide by 3, so the entire fraction is divisible by 3, so we can do that. So dy over dx equals 2y minus x squared over y squared minus 2x. That's a better answer than that. They're both correct. I wouldn't count either one wrong. As a general rule, you should always try to simplify your work as much as possible. So when you get a derivative, if you can make it simpler, you should try. Give me the correct answer and then start modifying the correct answer. If your correct answer is here and in your modification you mess up and get something wrong, and all they're asking for is a derivative, but you have the correct answer here, I'm going to give you full credit. I want to see you trying to get things simpler. Eventually you get to a point where as you continue trying, you'll get better and better at it, and eventually hopefully not make mistakes as you go. But always make the effort. The algebra in these problems does get pretty ugly. You know, the level of your ability compared to the ugliness of the problems should be about the same, but still sometimes they're a little intimidating. So anytime you get an expression answer, especially with the trig stuff, and you can maybe make it simpler, attempt to do that, and it makes for a better answer that you can work with more easily down the road.